Okay, here's another example for 4.1, a little more interesting. First thing we should be doing is talking about the domain of our function. And because we have natural log of x, we know that its domain is restricted to only positive numbers. Okay, so when we're looking for our critical values, they have to be a positive number. Okay, so if we're going to use the first derivative test, we need the first derivative so we can find our critical points. All right, so here we go. This is where the fun begins. Looking at this function, I'm going to use the product rule. I haven't done this for a while. Okay, product rule. So my first function is x, my second function is natural log of x. So product rule says derivative of the first times the second plus the first function times the derivative of the second. All right? Oops, that's my first derivative. All right, let's pretty that up. So 1 times natural log of x is natural log of x. What happens here when I take x times 1 over x, I get 1. Okay, so simplifying is going to be needed now many times because we are going to set it equal to 0. So to find the critical points, we have to set our first derivative equal to 0. Oh, flashback to college algebra. How do we solve these logarithmic equations? Okay, if you recall, we isolate the logarithm. So I have natural log of x equals -1. And then we have to rewrite this in exponential form. Is one way of doing it. Okay, so we're going to rewrite in exponential form. All right, so if you remember, natural log is base e. So it's something like this. Log base e of x equals -1. So if you remember this, e to this power gives me x. Right, so e to the negative first power is x, which is the exact value of my critical point. Okay, so my critical point is x equals e to the -1, or you could say 1 over e if you'd like. Okay, the other way you could do it is to raise each side yeah, that sounds weird. Maybe we should say exponentiate each side and write it with the base of e. So you could say e to the natural log of x equals e to the -1. And this is one of our inverse properties. Because the base on natural log and the base on the exponential function are the same, this becomes x equals e to the -1. Doesn't matter to me which one you use. I typically use this method myself. Okay? All right, so now we have our critical value, which 1 divided by e we know is a positive number, so it is a critical point in our domain. All right, what are we going to do? First derivative test. We want to know if it's a local max or min. All right. Oh, I ruined the fun. Darn it. Oh, well, we'll see. All right. Okay, so we can do the first derivative test, which requires our first derivative, which was natural log of x plus 1. Okay, and so we're going to do our number line. And one thing that's different now, I don't have an arrow here. Remember, our domain is 0 to infinity. So it starts at 0, goes to infinity. All right? So our critical value here is e to the negative 1. Or if you can always do a decimal, but we can do something pretty sweet where we don't really need our calculator. Okay? So let's choose a test value in each interval. Well, if this is e to the negative 1, then I could test e to the negative second, and I could test e to the negative third. That doesn't seem reasonable, does it? Okay, if you need to, turn them into fractions. So I actually need a positive exponent. So let's try e to the, let's try e to the positive second. Okay, you can check those in your calculator. All right, so what are we going to do? I'm going to just do the little work over here so we can see it. So if I test e to the negative second in my first derivative, that's the natural log of e to the negative second plus 1. So here's our properties again. Remember, this is log base e of e to the negative second. When these bases are the same, then the exponent there is our value. Because remember, this means what's the exponent on base e that gives me e to the negative second? Well, it's going to be negative 2, and negative 2 plus 1 is negative 1. So when I plug that test value in, I get a negative value. So my first derivative is negative on that interval. Okay, when I plug in e to the second, similar fashion, into my first derivative, I get the natural log of e to the second plus 1, which evaluates out to be 2 plus 1, which is 3, which is positive. So it is positive on this interval, which tells me then that my function is decreasing and then increasing. So by the first derivative test, I know that my critical point, e to the negative 1, is a local minimum. Okay, so if I want to find the exact ordered pair for that point, then it's at e to the negative 1, and then I have to plug that where? Into the original function. Back into the original, which I don't think it could hurt if we check that out. Never a bad thing to do stuff with exponential and log functions, I've found. All right, so my original function is x natural log of x. So when I plug in e to the negative first, I get e to the negative first times the natural log of e to the negative first. So this becomes negative 1. So I end up with negative e to the negative first. Okay. So that means that my critical point is e to the negative first, negative e to the negative first. Which, if you look at my fancy Desmos graph, by the way, you have to make it put the open circle. Remember, this function is not defined at 0. Okay? But I can see this is my min. This is e to the negative first, and this is negative e to the negative first. And I can see by the graph it's a local min. Goodbye.